From our calibration graph, we can see that it is a good linear relationship between absorbance and the concentration of standard solutions. The R-squared that represent the linear regression coefficient is 0.9996, which is close to 1 and shows the accuracy is 99.96%. This indicates that the model fits the data well, hence it can be concluded that the calibration data is accurate. We are quite confident with the exact type of beverage in the samples as we get the same results for 10 and 50 times dilution. However, there might be some error as some of the readings are concordant to each other. The samples were already well prepared beforehand, and so we do not know when they were prepared or how. It may contaminate and suspend after a period of time. Why higher dilution factor is better? For Beer-Lambert law to be obeyed, solution must be in low concentrations. The sample solution must be diluted so that it falls in the range of calibration standard graph, and hence concentration reading obtained will be more accurate. From this, we can conclude that the higher dilution factor gives a greater accuracy in concentration readings. Errors are likely to occur in every experiment and hence vary the outcome of the result, but it's important to avoid them at any rate. First, impurities in the sample may cause an error. The light entering the cuvette encounter the small particles or the grime and cause interference to occur and lead to a derailed value. Besides, plastic and glass cuvettes are cheap, but not suitable to use at ultraviolet regions of wavelengths under 280 and 320 nanometers respectively, because their absorbance is too high. The quality and condition of the cuvette is important for the measurements. In our experiment, the wavelength determined was around 270 nanometers, so this clearly indicates that the cuvette itself absorbs a certain amount of light entering. Fingerprints on the transparent side of the cuvette cause scattering of the incident light and hence affect the accuracy of the results in the experiment. Lastly, suspended bubbles in the sample can lead to a miscalculation. Since bubbles create cavity in the sample, it causes scattering light entering the cuvette. However, there are several ways to rectify the possible errors to achieve the most efficient analysis. To ensure complete removal of the previous sample in the cuvette, rinse the cuvette properly with distilled water, followed by drying the cuvette using compressed air or nitrogen. Washing the cuvette after each test is essential as the residue of the previous sample might combine with the next sample and potentially lead to an error. Fingerprints on the exterior transparent surface of the cuvette might affect the results as well. This can be improved by wiping the transparent side of the cuvette with a damp Kim wipe, followed by dry tissues. Gloves should be also worn throughout the experiment. The analysis can be improved by eliminating the air bubbles inside the cuvette. Tap the cuvette gently or use a needle to prick the air bubbles. If the air bubbles remain, rinse the cuvette with sample solution. The cover of the sample chamber should be closed completely to prevent light from entering the chamber and hence increase the accuracy. Another improvement is to use a quartz cuvette instead of a plastic cuvette. Quartz has a much better response in the UV region in which it doesn't absorb light below 380 nanometers. Moreover, place the UV vis spectrophotometer on a flat and level surface that is free of surrounding vibration to increase the efficiency of the instrument.
Created using Powtoon.